cs407 Numerical Analysis, Polynomial Interpolation. At 20 pages, this weighs in as the longest section in the book. It's an important topic and we'll be spending 2 days on it. I'll try to get through as much of it as possible here, but it is quite a weighty section. We can begin with a real-world example, and here we're going to look at the viscosity of water. So you can imagine we've done an experiment and we've measured the viscosity at different temperatures and put them in this table. So at 0 degrees it's 1.792, 5 it's 1.519, 10 1.308, and 15 1.140. What we can do is we can do polynomial interpolation to create a polynomial of degree 3 that assumes the values in this table. And what it'll also do is it'll let us calculate acceptable values for temperatures that are not in the table, so we can get an estimate of those. In this case, if we wanted to look at the polynomial value at 8 degrees, it would be 1.386 as an estimate of what the viscosity of water would be at 8 degrees centigrade. So let's take a look at how to do polynomial interpolation. Later in this chapter we'll perform numerical differentiation, and later in the book we'll use similar techniques to do splines and least square methods. For further motivation, we're going to start by looking at 3 problems that fall into these types of categories. So all 3 of these problems concern the representation of functions to give an indication of the subject matter in this chapter, chapter 6, and chapter 9. So problem 1 says, suppose we have a table of numerical values of a function. Is it possible to find a simple and convenient formula to reproduce the given points exactly? Problem 2 says, we assume that the table of given numerical values is contaminated by some error, such as if they came from physical environment or a physical experiment. How can we find a formula that represents the data approximately, and if possible filters out the errors? Problem 3 says a function f is given, perhaps in the form of a computer procedure, but it's expensive to evaluate. In this case, we want to find another function, g, that's simpler to evaluate and produces a reasonable approximation of f. In all of these problems, a simple function p can be obtained that represents or approximates a given table or function f. The representation p can always be taken to be a polynomial, although many other types of simple functions can be used. Once a simple function p has been obtained, it can be used in place of f in many situations. For example, the integral of f could be estimated by the integral of p, and the latter would be generally easier to evaluate. In many situations, polynomial solution to the problems outlined will be unsatisfactory from a practical point of view. Another class of functions can be considered. Later, one other class of versatile functions is discussed, and that's in Chapter 6, the spline functions. Right now we're going to be concerned with polynomials exclusively, and later we'll discuss general linear families of functions, of which splines and polynomials are important examples. So one of the important questions in numerical analysis is to ask, well, how can something fail? And the obvious way in which a polynomial can fail as a practical solution to one of these 3 problems that we discussed is that it has a degree that may be unreasonably high. So consider a table with 1,000 entries. We're going to need to have a polynomial of degree 999 that may be required to represent it. Polynomials may also have the surprising defect of being highly oscillatory, particularly at high n. Another problem is that the table values may be precise, but other points may be a poor approximation when you're using the polynomial to get those, particularly due to that high oscillation factor. Later in Chapter 7 we'll look at a example involving the range function that illustrates precisely this phenomenon. But it's now time to turn our attention to polynomial interpolation. And now that you've had a brief preview of the various techniques available for solving these problems, let's look at the main technique from Chapter 4, namely polynomial interpolation. We begin with a table of values and assume that the x sub i's form a set of n plus 1 distinct points. So here's our table. The x sub i's and the y sub i's are given in this table. Table represents n plus 1 points in the Cartesian plane in the form of coordinates x0, y0, x1, y1, all the way out to xn, yn. So what we're doing is looking to determine a polynomial that's defined for all x, and takes on the corresponding values of y sub I for each of the n plus 1 distinct x sub I in the table. A polynomial that does that is said to interpolate the table, and the points x sub I are called the nodes, and the y sub i's are the values of those nodes. So let's start with the easiest case, that's n equals 0. And here basically we can use a constant function to solve that problem. In other words, a polynomial p of degree 0 defined by p of x is equal to y0 reproduces the one node table. The second easy case is n equals 1, and there we have 2 points, and 2 points determine a line, and we can use the linear function to solve this. The linear function is given by this formula for p of x here. The equation in the second table is of first degree at most and reproduces the table. This means that px0 equals y0 and px1 equals y1. It's pretty easy to verify that. And this is known as linear interpolation. Now that we've seen the two easy cases, let's take a look at an example involving one of them. So, in this example, we want to find the polynomial of least degree that interpolates this table. This is an example of a straight line formula function. Here, we can just use the formula from the previous slide. And we use our formula, and we plug in the values for x1 and x0, and we plug in the values for y0 and y1, and place this in a form with x, and as a result we get 3.7 minus 4/3 times x minus 1.4. So the interpolating polynomial can be written in a variety of forms. Among the most well-known are the Newton form and the Lagrange form. Newton form is probably the most convenient and efficient. However, conceptually, Lagrange form has several advantages. And let's begin by taking a look at that Lagrange form. So, suppose we want to interpolate arbitrary functions at a fixed set of nodes x0, x1 through xn. First, define a system of n plus 1 special polynomials of degree n, which are known as the cardinal polynomials in interpolation theory. These are denoted L0, L1 through Ln, and have the property L sub I of xj is equal to delta ij, which is 0 if I is not equal to j, and 1 if I is equal to j. Now, you may recognize this as Kronecker delta property if you've seen that in linear algebra before, and that's precisely what it is for this Lagrange form. Once these cardinal polynomials are available, we can interpolate any function f by the Lagrange form of the interpolation polynomial. Specifically, Pn of x is equal to the sum from I goes to 0 to n of L sub I x times f of x sub I. This function, Pn, is a linear combination of the polynomials L sub I, and is itself a polynomial of degree at most n. When we evaluate Pn at x sub I, or x sub j, we get f of x sub j. Because again, we're making it model it precisely at those points. So Pn xj is equal to sigma I equals 0 to n L sub I of x, f of x sub I, which is equal to f of x sub j at the end. So P of n is the interpolating polynomial for the function at nodes x0, x1, xn. All we need to do now is write the cardinal polynomial formula, and we can write that as a product. You'll notice this formula is a product of n linear factors, and it can actually be written on an expanded form, such as one found on page 155 of the text. So here it is as a product of n linear factors. Now, the denominators here are actually just numbers because those are the x sub i's, and the variable x only appears in the numerator. So L sub I is going to be a polynomial of degree n, and when L sub I of x is evaluated at x equals x sub I, each factor in the equation becomes 1, so L sub I of x sub I is equal to 1. When L sub I of x is evaluated at any other node, say xj, one of the factors will be 0, and L sub I of xj is equal to 0 for I not equal to j. Let's take a look at the first few Lagrange polynomials. Well, here they are. You can see they actually cover quite a bit of range in this graph, and they're fairly different from one another. This will help us in forming interpolating polynomials. We'll take an example, take a look at an example to make things a bit clearer here. So, this example asks us to write out the cardinal polynomials appropriate to the problem of interpolating the following table, and give the Lagrange form of the interpolating polynomial. So, what we need to do is we need to use this form to get the cardinal polynomials, and this form is L sub I of x is equal to the product of j equals 0 to n of x minus x sub j, xi minus x sub j, for I runs between 0 and n inclusive, and I is not equal to j. So, let's get cracking. L0 of x is equal to, again, we're just plugging in the x sub I and x sub j, so it's x minus 1/4 times x minus 1 divided by 1/3 minus 1/4, and the result is 18 times x minus 1/4 times x minus 1. We do the same thing for L1 and for L2. Now, we'll need the values of f of x sub I, which are 2, minus 1, and 7 respectively from the table on the previous slide. And we're going to multiply those times the L sub i's. So, therefore, the interpolating polynomial Lagrange form is minus 36, which is 2 times 18, times x minus 1/4 x minus 1, minus 16x minus 1/3 times x minus 1, which is minus 1 times L1, plus 7 times L sub 2, which is 14x minus 1/3 times x minus 1/4. It's a mouthful anyway. Apart from combining some fairly nasty functions, though, the procedure is fairly straightforward and a lead-you-by-the-nose affair. The Lagrange interpolation formula provides the existence of an interpolating polynomial for any table of values. It's another constructive way of proving this fact, and it leads us to a different formula. So let's take a look. Suppose that we have succeeded in finding a polynomial p that reproduces part of the table. Assume p of xi is equal to y sub I for the first k values. Now, let's add another term to p that will enable to reproduce one or more entry in the table. P of x plus c times x minus x0 times x minus x1 all the way out to x minus x sub k, and c is going to be our constant to be determined. Now, this new equation is still a polynomial. It also reproduces first k points through p of x in the table because p itself does so. And the added portion takes value 0 at each of the points x0, x1, xk. So, its form is chosen precisely for that reason. Now, we just adjust it, c, so that the new polynomial takes value yk at xk plus 1. The proper value of c can be obtained from this equation because none of the factors xk plus 1 through minus xi for 0 for I from 0 to k can be 0. Remember our original assumption that the x sub i's are all distinct. This analysis is an example of inductive reasoning. We've shown this process can be started and that it can be continued. Hence we can make the following formal statement that tells us the existence of an interpolating polynomial. Namely, Theorem 1. If the points x0, x1 through xn are distinct, then for arbitrary real values y0, y1, yn, there's a unique polynomial p of degree at most n, such that p x sub I is equal to y sub I, for I running between 0 through n. Now, the degree of the polynomial increases by at most 1 in each step of the inductive proof, so the final is of degree at most n. Any other polynomial q that accomplishes what p does is going to end up being equal to p. So that wraps things up for the Lagrange form. You can see a few more details on these notes on page 157 of the text, and now it's time to take a look at Newton's form of the interpolating polynomial. So in the second example, we found this rather nasty equation for p2 of x, namely minus 36 times x minus a quarter times x minus 1 minus 16 times x minus 1/3 times x minus 1 plus 14 times x minus a third times x minus a quarter. We can further, quote, simplify this to minus 79/6 plus 349/6x minus 38x squared. We can also express this polynomial in a form called the nested Newton form. The Newton form involves the fewest arithmetic operations and is recommended for evaluating p2 of x. It cannot be overemphasized that the Newton and Lagrange forms are just two different derivations for precisely the same polynomial. Newton form has the advantage of the easy extensibility to accommodate additional data points. Let's take a look at an example of a method known as Newton's algorithm, which will result in a polynomial that is in the Newton form of the interpolating polynomial. So again, we have a example table, and we want to find the interpolating polynomial of least degree. In this algorithm, we're going to generate 5 polynomials: p0, p1, p2, p3, and p4. Now, the first one's going to be really easy. In particular, p0 of x is equal to minus 5. Now, p1 is going to have the following form. p1 of x is p0 of x plus c times x minus x0. And we know p0 of x is minus 5 plus c times x minus 0, because x0 is 0, with p sub 1 of 1 is equal to minus 3 here. So, minus 5 plus c is equal to minus 3, and we can easily get that c is equal to 2. So p1 of x is minus 5 plus 2x. We'll continue this on the next slide. So far we have that p0 of x is minus 5 and p1 of x is minus 5 plus 2x. Find p2, and p2 of x is p1 of x plus c times x minus x0 times x minus x1, and we get minus 5 for minus 5 plus 2x for p1 of x, plus c of x, because again x0 is 0 and x1 is 1, so it's cx times x minus 1. And p2 evaluated minus 1 is minus 15, so from the table, and so we get minus 5 plus 2 times minus 1 plus c times minus 1 times minus 1 minus 1 is equal to minus 15, and after a bit of algebra we get out that c is equal to minus 4. And so p2 of x is minus 5 plus 2x minus 4x times x minus 1. The remaining steps are similar, and we end up with p4 is minus 5 plus 2x minus 4x times x minus 1 plus 8x times x minus 1 times x plus 1 plus 3x times x minus 1 times x plus 1 times x minus 2. And it's not as bad as the procedure for Lagrange, in my opinion. Later we're going to develop a better algorithm for constructing the Newton interpolating polynomial. Nonetheless, the method just explained as a systematic one involves very little computation. An important feature to notice is that each new polynomial is obtained from its predecessor by a new term. Thus, the final polynomial exhibits all the previous polynomials as its constituents. So, for example, here you can see p of 0, p of 1, p of 2, p2, all the way out to p4. So, now, let's rewrite the Newton form of the interpolating polynomial for efficient evaluation. We'll do this by way of example. So what we're going to do is we're going to rewrite the polynomial from last example in the nested form and use it to evaluate p4 of 3. So you'll recall that p4 of x is equal to minus 5 plus 2x minus 4x times x minus 1 plus 8x times x minus 1 times x plus 1 plus 3x times x minus 1 times x plus 1 times x minus 2. We can rewrite that in a nested form, similar to what we did in section 1.1. And then we can actually go about evaluating that using nested multiplication, and we get a result of 241. This form is obtained by expanding and systematic factoring of the original polynomial. It is also known as a nested form, and its evaluation is by nested multiplication. We'll need to describe this in a formal way if we're going to attempt to use it in an algorithm, which we are. So, formally, to describe nested multiplication in a formal way, we consider a general polynomial in the Newton form. For example, p of x is equal to a0 plus a1, x minus x0 plus a2, x minus x0 times x minus x1, all the way out to an, x minus x0, x minus x1, x minus xn minus 1. And we can write that in a nested form, similar to what we did in chapter 1. And we'll see how to now succinctly write the Newton interpolating polynomial. We can write the Newton interpolating polynomial succinctly as Pn of x is equal to the sum I equals 0 to n of a sub I times product j equals 0 to I minus 1 x minus x sub j. And we're going to interpret j equals 0 to minus 1 of x minus xj is equal to 1. We can also write the product portion as pi sub I to make it even more compact, so p sub n of x is equal to sigma I equals 0 to n a sub I times pi I of x. This figure shows the first few Newton polynomials, pi 0, pi 1, pi 2, pi 3, pi 4, and pi 5. In evaluating p of t for a given number, we start with the innermost parentheses and work our way out as follows. v0 is equal to an, v1 is v0 times t minus xn minus 1 plus an minus 1, all the way down to vn, which is vn minus 1 times t minus x0 plus a0. At the end of the calculation, vn is now going to take on the value that p would take on at point t. Let's write some pseudocode to see how we can do this evaluation in the interpolating polynomial. So here's our pseudocode, and again we just have one for loop here, and we're going to have v continually take on that value through an assignment statement. The array A is going to contain the n plus 1 coefficients of the Newton form of the interpolating polynomial, and the array X is going to contain the n plus 1 nodes of x sub I. Of course, I is going to take on the I values, and V will contain the result of the polynomial evaluated at point T, and n is going to be the degree of the polynomial, so we're going to go all the way from n minus 1 down to 0, going in reverse for that loop. Now let's look at how to determine the coefficients efficiently. To do this, we're going to use a technique called divided differences. So we now turn to the problem of determining these coefficients, a0, a1, an efficiently. Again, we start with the table of values for the function f. Now here the points x0, x1, x2, all the way out to xn are assumed to be distinct, but no assumption is made about their position on the real line. In other words, they don't have to go in order. Previously we established that for each n equals 0 to 1, etc., there exists a unique polynomial Pn such that the degree p of n is at most n, and Pn of xi is equal to f of xi for I equals 0 through n. Crucial observation about p of n is that the coefficients a0, a1, etc. do not depend on n. In other words, p of n is obtained from p of n minus 1 by adding one more term without altering the coefficients already present in p n minus 1 itself. This is because it can be expressed in the form Pn of x is equal to Pn minus 1 of x plus a sub n times x minus x0 all the way out to x minus x sub n minus 1. So a way of systematically determining the unknown coefficients a0, a1, an is to set x equal in turn to x0, x1, xn in the Newton form and to write down the resulting equations. And here they are. Note that we can write this in a much more compact form, such as one found on page 161 of the text, although a lot of times it's useful to have the expanded form. And then we can solve the a sub i's in turn, starting with a0. We solve the a sub i's in turn, starting with a0. We see that a0 depends on f of x0. a1 depends on f of x0 and f of x1, and ak will depend on the values of f at the nodes x0, x1, all the way out to xk. Traditional notation is a sub k is equal to f of x0, x1, xk, which is called the divided difference, because of and we use those square brackets, of order k for f. The a sub I are uniquely determined by the equations on the previous slide. As a0 is f of x0, a1 is f of x1 minus a0, divided by x1 minus x0. Page 161 has the divided difference form for a2. If you want to see its long form, it's a longer equation. But let's take a look at an example of how this works. So here I want to determine the divided difference f of x0, f of x01, f of x0, x1, x2 for this table. Well, what we do is we write out the equations. F of x0 is equal to a0. So 3, f of x0 is 3, is equal to a0, and we have a0 equals 3. F of x1 is a0, which we knew was 3, plus a1, x1 minus x0, which is 3 plus a1 times minus 4 minus 1. And that's going to be equal to f of x1, which is 13. And basically 13 is a0 plus a1 times minus 5. And f of x2, we can again solve that by writing out the long form, plugging in the a0s and the x's sub i's that we know, and at the end of the day we get a0 is 3, a1 is minus 2, and a2 is 7. So here are our divided differences. With this new notation, the Newton form of the interpolating polynomial takes the form Pn of x is equal to the sum of the divided differences times the product of x minus x sub j, with the product j equals 0 to minus 1, x minus x sub j is equal to 1, when j is runs from 0 to minus 1. Divided difference can actually be calculated rather recursively. Through a rather nasty equation that you see here on the bottom. This one is labeled as equation 9 on page 162 of the text. And it's one of the reasons we're going to let the computer take care of things through an algorithm. Don't worry, I'm not going to make you memorize this one. So let's take a look at the algorithm for doing this. So what we do is the algorithm for computing the divided differences of f. We set f of x0 equal to f x0. For k equal to 1, 2 through n, we compute f of x0, x1, xn, that divided difference, by the equation. And it's pretty easy to program with appropriate loops, and computes the divided differences with 1/2 n times 3n plus 1 additions, n minus 1 times n minus 2 multiplications, and n divisions. This operation count does exclude arithmetic operations on the indices if we have to do lookups. Now, while this works, there's a more refined method that uses fewer operations line of the code. It's only going to require 3 statements, and it's only going to cost 1/2 n times n plus 1 divisions and n times n plus 1 additions. Nope, it's not Haskell, but it does involve a recursive property. Now let's take a look. And this recursive property is given in Theorem 2. The divided differences obey the recursive formula. Divided difference of f of x0, x1, xk is equal to f of x1 through xk minus f of 0 through xk divided by xk minus x0. Notice that x0, x1 through xk, the divided difference, does not change if the nodes are permuted. So for example, the divided difference of x0, x1, x2 is the same as the divided difference of x1, x2, x0. The reason is that the coefficient f x0, x1, x2 is the coefficient of x squared in the quadratic polynomial, interpolating f at x0, x1, x2. Whereas f x1, x2, x0 is the coefficient of x squared in the quadratic polynomial, interpolating f at x1, x2, x0. These two polynomials are, of course, the same. This leads us to the invariance theorem that says the divided difference is invariant under all permutations of the arguments x0, x1 through xk. Since they're arbitrary, we can rewrite the recursive formula. And you can also find the first 3 divided differences on page 164 of the text as part of the proof of this invariance theorem. We can also construct the divided differences table. Now this table is actually going to be valuable for expressing the Newton form, because the coefficients along the top diagonal here are actually going to be the ones needed to form the Newton form in the interpolating polynomial. The other ones are valuable to calculate, and we'll see how to do that because they form the next ones. But the ones that we need are these 4. Let's take a look at how to construct this divided difference table using an example. And then we'll get to the algorithms in pseudocode. So, what we'd like to do is construct a divided difference diagram for the function f given in the following table, and write out the Newton form of the interpolating polynomial. Here, we calculate the divided difference table. The first column is, as you saw in the last slide, is just going to be fx0, fx1, fx2, and fx3, which are going to be the values in the table for fx. So, that one will be fairly easy. For column 2, the first entry is fx0x1 is fx1 minus fx0 times x1 minus x0, and basically here fx1 is 13/4, f of x0 is 3, so it's 13/4 minus 3, x1 is 3/2, x0 is 1, and we put that in and we get 1/2. Now for column 2, the other 2 entries, we continue along using our formula, and we plug in the numbers. We get 1/6 and minus 2/3. Column 3, again, we use the formula and our previous results, and we derive the values 1/3 and minus 5/3. Now, I performed all the calculations here. They don't do that in the book. It's good practice for you to do the same, even though we're just going to use the upper diagonal. It's good to get all the values in the table because you use them to get that upper diagonal. Well, now that we're done having fun with fractions, let's take a look at the completed table. And here's the completed table. Notice we're going to use the main diagonal here to get P3 of x using these coefficients. Pretty nifty. So finally, we're going to turn our attention to the algorithms in pseudocode. Here's the divided difference pseudocode. We suppose the table f is given at the points x0, x1 through xn, and all the divided differences aij are equal to the divided differences f of x1, x plus 1, x to j are to be computed. Observe that the coefficients of the interpolating polynomial are stored in the first row of the array aij up here. That's an n by n array. So can be a bit more space efficient with A if you only store the divided difference needed for the interpolating polynomial and do that in a single dimensional array, which will provide the same calculations but with less space. We'll see this forms the basis of one of our two main routines for solving these interpolation problems called Coef. So here's the Coef pseudocode, and again it's going to use that single dimensional array. It's a little more detailed and tricky than the straightforward calculation with the n by n array. And Coef requires as input a number n and the tabular values x sub I and y sub I. Remember that the number of points in the table is n plus 1, and the procedure then computes the coefficients required in the Newton interpolating polynomial and stores them in the array A. After we're done with the coefficient calculation, we can actually evaluate things. And since you have the interpolating polynomial from the Coef routine, you only have to call eval after the first use of Coef, and just change t if you want to do additional evaluations. And now what it requires is the input array x sub I from the original table, and the coefficient array from the output of the coefficient subroutine. The array a sub I contains the coefficients for the Newton form of the interpolating polynomial. Finally, as input, a single real value for t is given. The function then returns the value of the interpolating polynomial p at t. Since the coefficients of the interpolating polynomial need to be computed only once, we call Coef first, and then all subsequent calls for evaluating the polynomial are accomplished with eval. See an example of how to do this. So, what we do is we create the pseudocode for the Newton form of the interpolating polynomial p for sine of x at 10 equidistant points in the interval 0 through 1.6875. We'll use this code to find the maximum value of the absolute value sine of x minus p of x over a finer set of equally spaced points in the interval. So, and that'll give us an approximation of the error. If we take 10 points, including the ends of the interval, we create 9 subintervals, each of length 0.1875. The points are then xi is equal to I times h for I equals 0 through 9. After obtaining the polynomial, we divide each subinterval into 4 panels, and we evaluate sine of x minus p of x at 37 points called t in the pseudocode. These points are xj is equal to j times h divided by 4, for j goes through 0 through 36. On the next slide we'll see the main pseudocode that calls the procedures Coef and eval given for this function. The first coefficient in the Newton form of the interpolating polynomial is going to be 0, and the others range in magnitude from 0.99 to 0.18 times 10 to the minus 5th. The deviation between sine x and p of x is practically 0 at each interpolating node, and you would expect that because it's going to hit those nodes when it draws the interpolating function, because those are the ones we're evaluating on. Because the round-off errors are not precisely 0. And for the computer output, the largest error is going to take place at j equals 35, where sine 1.640625 is approximately 0.9975631 with an error of 1.19 times 10 to the minus 7. This brings us to the Vandermonde matrix. You may remember this as an ill-conditioned and kind of evil matrix from chapter 2. So, the letter that you're going to see here is phi, and the phi's in the book look a bit different from the ones in Microsoft Office. Another view of interpolation is that for a given set of n plus 1 data points, x0, y0, x1, y1, through xn, yn, we want to express an interpolating function f of x as a linear combination of a set of basis functions, phi0, phi1, phi(n), so that f of x is approximately c0, phi0 of x plus c1 times phi1 of x plus cn times phi(n) of x. Here the coefficients are to be determined. We want the function to interpolate the data xi, yi. So we will have a linear equations of the form f of xi is approximately c0, phi0 of xi plus c1, phi1 of xi plus cn, phi(n) xi is equal to y sub I for I equals 0 through n. Furthermore, these linear equations of the form fxi is equal to c0, phi0 xi plus c1, phi1 xi plus cn, phi(n) xi is equal to y sub I for I is 0 through n. These form a system of linear equations, AC equals y, and here the entries in the coefficient matrix are given by a sub I j is equal to phi j times evaluated x sub I, which is the value of the jth basis function evaluated at the ith data point. The right-hand side vector y contains the known data values y sub I, and the components of the vector c are the unknown coefficients c sub I. So, the simplest way to do this, the most common basis functions are polynomials, and the natural basis for the polynomials consists of the monomials. And the monomials are 1, x, x squared, x cubed, all the way out to xn. And these are the basis for the polynomial functions. The graph here shows the first 5 monomials: 1, x, x squared, x cubed, and x to the 4th. Consequently, a given polynomial Pn has the form P sub n of x is equal to c0 plus c1x plus c2 x squared plus c sub n x to the n. And the corresponding linear system, AC equals y, has the form shown on the slide. Now, this coefficient matrix is called the Vandermonde Matrix. It can be shown that this is non-singular, provided that their points x0, x1, xn are distinct. So, in theory, it's invertible, and we can solve the system for polynomial interpolant. Although the Vandermonde matrix is not singular, it's still conditioned as n increases. For large n, the monomials are less distinguishable from one another. Moreover, the columns of the Vandermonde matrix become nearly linearly dependent in this case. Most importantly, high-degree polynomials often oscillate wildly, and they're highly sensitive to small changes in the data. So, is there an alternative? Hey, it's that guy from Lab 1, Chebyshev. So far we discussed 3 choices for the basis functions: the Lagrange polynomials L sub I of x, the Newton polynomials pi sub I of x, and the monomials. Chebyshev polynomials are also an excellent choice, and they have several special properties such as this recursive relation where t0 of x is equal to 1, t1 of x is equal to x, ti of x, for x greater than 1, is 2x times ti minus 1 of x minus ti minus 2 of x. So, here's the first 5 Chebyshev polynomials. These curves for these polynomials are quite different from one another. Chebyshev polynomials are usually employed in the interval minus 1 to 1, as you can see on the graph. With changes of variable, they can be used on any interval, but the results will be a little more complicated. One of the important properties of these is the equal oscillation property. Notice in the figure that successive extreme points of the Chebyshev polynomials are equal in magnitude and they alternate in sign. Property tends to distribute the error uniformly when the Chebyshev polynomials are used as basis functions. In polynomial interpolation for continuous functions, it's particularly advantageous to select as the interpolation points the roots or the extreme points of the Chebyshev polynomial. This causes the maximum error over the interval of interpolation to be minimized. We're going to have these reappear in Chapter 9, but now it's time to turn our attention to a process called inverse interpolation. And inverse interpolation is a process to approximate an inverse function. So suppose that the values yi equals f of xi. have been computed x0, x1, xn using this table. We can form the interpolation polynomial in our usual way. P of y is equal to the sum I equals 0 to n, ci, the coefficients, times the product y minus y sub I. The original relationship y equals f of x has an inverse under certain conditions, and this inverse is approximated by x equals p of y. So basically what we can do is we can use Coef and Eval to carry out the inverse interpolation simply by reversing the arguments x and y in the calling sequence of Coef. Inverse interpolation can be used to find where a given function f has a root or a 0. This means inverting the equation f of x is equal to 0. Propose to do this by creating a table of values f of xi, comma xi, and interpolating with the polynomial p. Thus p of y sub I is equal to xi. The points x sub I should be chosen near the unknown root r. The approximate root is then given by r is approximately equal to p of 0. The figures here show an example of a function y equals f of x and its inverse function x equals g of y with the root r equals g of 0. Let's take a look at an example. For the table of known values, find the inverse interpolation polynomial. Well, again, what we can do is we can plug that into our code and reverse the x and y. And the solution is the nodes in this problem are the points in the row of the table headed yi, and the function values being interpolated are in the x row. So we reverse the x and y. And with our routine, we plug that in and we get some rather nasty looking numbers, but the important thing is we can get p of 0 is 4.247470086, and we have our interpolating polynomial. Take a brief look at Neville's algorithm, which provides us for another method for obtaining polynomial interpolate from a table of values. So Neville's algorithm is another example of obtaining polynomial interpolate from a given table of values. It builds polynomial in steps just as Newton's algorithm does. Constituent polynomials have their own interpolating properties of their own and are defined by recurrence relations. You can see these relations on page 170 and 171 of the text. There's also a theorem that gives the interpolating properties of the polynomials generated by this method. We're going to see these reappear when we develop B-splines in section 6.3 of the text. The pseudocode for Neville's algorithm is here. We probably won't be using in this section, but if you do need it, it's there. And lastly, interpolation of bivariate functions. Basically, what we've discussed so far is for one variable. By polynomials extended to some cases, can be extended to some cases where the functions have two or more variables. An important case occurs when a function xy gets mapped to the value given by the function f of xy, and we want to approximate it on a rectangle. This is known as a tensor product interpolation. So, suppose the rectangle is the Cartesian product of two intervals ab times alpha beta, or cross alpha beta. That is, the variable x and y run over the intervals alpha beta, or ab and alpha beta respectively. And what we can do is we can use the Lagrangian polynomials to create an interpolation of two variables. If you want to do that, the formulae are found on page 172 and 173 of the book. Next time we're going to look at errors in polynomial interpolation. This will be a significantly shorter section.